Now I'm going to be working example 4 from page 198 in your textbook. So page 198 in your textbook, and I'm going to be working example 4. It says, a spy uses a telescope to track a rocket launched vertically from a launching pad 6 kilometers away. See figure 6. At a certain moment, the angle, theta, between the telescope and the ground is equal to pi over 3 and is changing at a rate of 0.9 radians per minute. What is the rocket's velocity at that moment? The picture that you can see in your textbook is that there is a rocket being launched vertically. Someone is 6 kilometers away, and they're looking through a telescope at the rocket, and there's this angle theta right there, and this obviously forms a right angle. Your book calls this distance over here y, and I'm going to call this distance here x. So the 6 kilometers is distance x. Let me move this over. X equals 6 kilometers. So let's go through and see what kind of information that we can get. It says the spy uses a telescope to track a rocket launched vertically from a launching pad 6 kilometers away. We already have that in our picture. A certain moment, the angle between the telescope and the ground is equal to pi over 3. So at this moment, theta is pi over 3. That is this angle right here is pi over 3 at this moment. And is changing at a rate of, so change, rate, those are good clues, 0.9 radians per minute. And you see the radians per minute. There's a change in angle with respect to time. So the change in angle with respect to time is 0.9 radians per minute. That's a d theta dt because it's a change in angle with respect to time. And then the question is, what is the rocket's velocity at that moment? Well, remember, this rocket is moving up, right? So the rocket's velocity is going to be going up. So it's how fast is this thing going up? Well, how fast this thing is going up will tell us the change in y with respect to time. That is what we're looking for. The rocket's velocity will be however fast that distance that the rocket is off the ground is changing with respect to time. If the rocket is going 500 kilometers per second, then this would be a distance, or the rate of change rather would be 500 kilometers per second. Now we need, once again, a formula that connects every single one of these things. So if you look, we have an angle right here. And the things that we know from this angle, we have some information, or at least we're concerned about information, that is opposite of that angle. We were given information about this side that is adjacent to that angle. So if we start to talk about the opposite side y compared to the adjacent side x, hopefully when you hear opposite over adjacent, your mind is automatically triggered from your trigonometry days to think of the trig function tangent. And it is the tangent of that theta that would be opposite over adjacent. And so here everything is all together in a nice formula, right? Now, before we start using this formula, hopefully you can see that we're going to need to know what this distance y is. So I'm going to begin by actually figuring out what y is at this moment. Well, I'm going to come over here to the side and do this in blue. The tangent of the angle right now is pi over 3. We don't know what the value of y is, but at this moment our x value is equal to 6. So tangent of pi over 3 has to be equal to y over 6, and so to get y by itself, we simply need to multiply by 6 on both sides. So y is equal to 6 times the tangent of pi over 3. If you use your calculator, making sure that you're in radian mode, down to radian and hit enter. And then we want to put in the tangent of pi divided by 3, close off our parentheses, and then multiply by 6. And I got that y should be equal to 10.39. So that's important information that we're going to need. Now, when we go to take a derivative, there are going to be several things at play here. Since we have a theta, we have a y, and we have an x, whenever we take a derivative, we're going to need a d theta dt, a dy dt, and a dx dt. So dx dt. As time elapses, how far is the distance from the telescope to the launch pad going to change? And the answer is, it's not going to change. The rocket took off from right here, is going directly up, and the telescope is still right here. So there is no change in this distance x right here. X is going to be constant, so the change in x with respect to time is equal to 0. Now, I haven't done this yet, and so I want to make sure I'm perfectly clear on how to work with this. This is a special case, okay? I do not like to plug in for any of the values before we take a derivative. I hate to plug in for any of the values before we take a derivative because it can be slightly confusing. So I'm going to do it for ease, and I may try to continue to do it, but I need to be very clear about when you can plug in before you take a derivative. These constant values that we have right now, y is 10.39, x is 6, and theta is pi over 3, cannot be plugged in before you take a derivative unless there is one case where you can actually plug in the constants before you take the derivative, and that would be in the case that the rate of change for that thing is equal to 0. If and only if the rate of change for one of the variables is equal to 0, can you plug it in before you begin to take a derivative? So since dx dt equals 0, we can take this value for x, since it's going to remain constant as we work the problem, we can go ahead and plug it in right now for x. Remember, only if the rate of change is equal to 0 can you plug in a constant before you take your derivative. So tangent of theta should be equal to y over 6. Simply plugging in the 6 for the x, and that is how we get this equation. And now we're going to take our derivative. The derivative, once again, needs to be taken with respect to time, and you'll notice that we don't have a t anywhere in the equation. So when we go to take the derivative of tangent with respect to time, the derivative of tangent is secant squared. So this will be secant squared of theta. But then because we use the wrong variable, our implicit differentiation means that we're going to have to multiply by d theta dt at the back equals. I'm going to use a quotient rule in order to take the derivative of y over 6. If you know the easier way to do this, then you can do it. But the quotient rule says we want to take low, which is 6, times the derivative of the top. And in this case, the derivative of the top is dy dt minus the top, high, which is y, times the derivative of the bottom, which will be 0, all over low squared. And the bottom squared will be 36, because 6 times 6 is 36. So I'm going to simplify some things over here on this right side of the equation. And so secant squared theta d theta dt, I'm going to leave alone. And this negative y times 0 is just going to cancel out, because anything times 0 is 0. And then you'll notice that we have a 6 on top right here and a 36 on bottom, and 6 will go into both of those. So it'll go into the top once, and so the top now just becomes dy dt all over. And if we divide the bottom by 6, we get 6. The question was asking us to find the velocity of the rocket, which we've already identified as dy dt. Everything else we need to plug in for right now. So d theta dt is 0.9 radians per minute. Theta right now is pi over 3. And y, remember we found earlier to be 10.39. But we don't even need y, do we? All right. So secant squared of theta, which is pi over 3, times d theta dt is 0.9 equals dy dt divided by 6. And so now to get dy dt by itself, I'm going to multiply by 6 on both sides. Cancels over here. And so dy dt is equal to 6 times secant squared of pi over 3 times 0.9. Now, with the secant squared, it's a little tricky to get secant squared into your calculator. But if you remember the trig identity that the secant of x is equal to 1 over cosine of x, then the way you're going to put this into your calculator is you're going to enter 1 over cosine of pi over 3. And then you're going to take that answer and square it. So if you put in 1 divided by the cosine of pi over 3 and close off your parentheses and hit enter, you get 2. Well, we need to take that number and square it. So we can just simply hit the squared button. And so we get that secant squared is 4. Secant squared is 4. When our angle is pi over 3. And so now if we just simply multiply 6 times 4 times 0.9, we get that dy dt is 21.6. Our unit of measurement in distance right now is in kilometers, and this is a rate of change, so it's going to be kilometers on top, over our change in time in this problem is measured in minutes. If you remember that from the fact that they told us that the change in theta with respect to time was 0.9 radians per minute. So this should be kilometers per minute. And how fast that distance y is changing is equivalent to the velocity of the rocket. And I just want to point out that earlier I found y in the very beginning. And then when we got to the end of the problem, it turned out that we didn't even need it, right? But in some situations, you will need that opposite side, and so it's good to know how to find it, though in this case, it was completely useless and an utter waste of your time, and for that I apologize. But nonetheless, the answer to our problem is 21.6 kilometers per minute.